Say again? You don't feel like a chemist today?
I do feel like
Oh, you do feel like a chemist. That's good. It's a good feeling, isn't it?
It just won't stand.
So I have one electron and it sits in S orbital, and I'm asked to determine the term symbol for the ground state. Alright? So, good job. Can I do that? Well, let's try. For this S electron, I have L equals 0, because it sits in S orbital, right? And little s equals 1/2. That is always true. Little s is always 1/2 for an electron. No exceptions. So that means that what I'm having here is an S as the letter for the term symbol, because the S corresponds to this guy, which has value 0. The J, the little j, equals L plus S. There's only one combination I can make, which is 1/2. That's why 1/2 goes right here. And the multiplicity is 2s plus 1, which is 2. So that is the term symbol. Hopefully you can do this now. Okay? It's just taking the steps and writing it down. I don't know what other term symbol I can come up with. This is just following these rules and oops, there it is. Okay, then something's happening to the sodium atom because the electron is excited to a higher state from the 3s to the 4d. That's where it's going. So the new configuration is basically, it sits in the 4d orbital. Question, of course, is very predictable. Now what is the term symbol? So this is the ground state, but now it's no longer in a ground state, it's now in an excited state. Okay, so just to visualize that, initially I was in the 3s, there's 3p orbitals and so forth, but what I'm going to is the 4d. There's of course 5 of these things, and I'm going to go from here to any of these, let's say this one. So the new configuration is neon 4d1. That is the electron configuration. To determine the term symbol for this, is it difficult to do? Not so much. Not if you are a real chemist. This is something you can tell anybody at any time, and people will be impressed. You meet somebody in a bar, you say, did you know the term symbol of sodium in its excited state is this? And people are like, oh, you are just amazing. How do you even know that? L equals 2. Why? Because it's in a d orbital now, and it has always L equals 2. In fact, L equals 2 equals the definition of a d orbital. It is the definition of a d orbital. L equals 2. S, still a half. What is J? Now I have two combinations. Because L is no longer 0, I can have 2 minus 1/2, which happens to be 3/2. And I can also have 2 plus 1/2, which is 5/2. So those are the two combinations. So I have at least 2 term symbols. What are they? They are both D, because that's what L is. L doesn't change. L is D. One of them is 3/2 for J. The other one is the same, but now with J equals 5/2, as I just determined. What is the multiplicity? It's 2s plus 1. S is always half if you have one electron, so it's 2. These are the term symbols for this excited state. Next question. The orange glow of older streetlights is due to the emission of an electron that sits in the 3p orbital and it falls down to a lower lying orbital. What are the term symbols for the possible final states, and how many lines do you expect? Okay, let's visualize this. That's helpful. Okay, so I have my 3s, then I have 3p. Okay, and apparently the electron sits in the 3p. The ground state we just determined is s2 1/2. Now, what is this state? Where it starts from? Okay, I want the term symbols here as well. I'm going to determine them very quickly. I can do it the same way as before. L equals 1 now. S equals 1/2. J therefore equals 3/2, comma 1/2. And therefore the two term symbols are P2 1/2 and P2 3/2. We've seen this answer before. The P is there because it sits in a P orbital, which is P, capital P. And then I have two values for J, 1 plus 1/2, 1 minus 1/2, so 3/2 and 1/2. Those are the two term symbols. So what happens now is that this electron will fall down to a lower lying state. The only state available is the S. That's an allowed transition because delta L is -1, which is an allowed value for an optical transition. So that's good. So that's the transition I'm talking about, from here to here. Let me just write this more explicitly, because this one is the real way of showing it. There are two energy levels. This one is doubly degenerate, this one has 4 states, total of 6. There's 6 states when an electron occupies a 2p or 3p orbital, because there's 3 orbitals, there's 2 orientations for spin, so it's 6 possibilities, and it's the same 6 possibilities as here. Okay, 4 for the top, 2 for the bottom. This is 2-fold degenerate, 4-fold degenerate, so a total of 6. But this is now written in terms of the term symbols. This is helpful because now I can predict the number of lines. The electron can be either in this state or in that state. We don't know where it is. If it sits in this one, it falls down here. If it sits in that one, it falls down there. And those are the 2 allowed transitions. There's going to be 2 lines. 2 lines. Did you have a question? No. Okay. So it's a doublet. So the answer to this question is the ground state or lowest lying state is ground state that we just figured out in question A. And there's going to be 2 lines expected. Yes?
Can you please go over one more time how you got L equals 2 on part B? Is it -2?
No. It has nothing to do with N. All of the term symbol stuff has nothing to do with N. Okay? Erase that from your mind right now. Take it out. There. It has only to do with the values of L and S. Okay? And this capital letter is, in the case of 1 electron, equal to little l. Whatever little l is what this capital letter is going to be in the term symbol for a 1 electron system. Not true for a 2 electron system, but for a 1 electron system is here, yes. So, L equals 2 because it sits in a d orbital. That's it. It doesn't matter if it sits in a 4d, in a 5d, or a 6d, because n is not important. You only focus on the values for the angular momentum, orbital angular momentum, L, and spin angular momentum, S. Those are the 2 you want to focus on.
They are degenerate, but then why is it higher than the other? Just split
Glad you
it.
brought that up because I think more people will be confused by it, but yeah, N is not part of this discussion at all. Who's ready for problem 7? I see 1 person, yes! That's a go for me. All right,
I'm also reacting.
let's talk about the hydrogen atom. The system is in the ground state, it says. First question, oh, this is an early one. Calculate the most probable radius of the electron. How do you do that again? You have to look at the,
Isn't it the like derivative of R of that PR?
yes, correct. Okay, so what I do is PR is this R function, and then I have this guy, and it's actually squared. Capital R is the radial wave function. And little r is there too. Hopefully you can see that. It's not like clear from far away. It's an r with a square. That is the radial distribution function. And what I have to do is I have to first write it out for this function, for this ground state of hydrogen, and then take the derivative, set it to 0. So that's what I have to do. I'm going to go to the table. I'm going to see what r is. I'm going to square it. And then I'm going to put an r squared in front of it. So if I do that, I get the following result. There's your r squared. And here's a function. It's a decaying exponential of the wave function. Minus 2r A0, which is the Bohr radius. My task is to take the derivative of this guy and then set it to 0, find the roots. So if I do that, if I have to do that, I have to, of course, use my abilities to take a derivative of a function that is composed of two things that depend on r. So there's two functions that depend on r squared and this decaying exponential. And so I have to use the product rule for taking the derivative, but fortunately, I can do that. And if I do that correct, and I assume you can, you'll be getting this. And that should be equal to 0. Oops. I made a mistake. It's r divided by a0. So the question is, when is this statement here, this equation 0? That is 0 when this one is 0, which is at infinity, doesn't count, that's not the most probable radius. Or when r equals 0, no, the most probable radius is not at the nucleus, somewhere in between. Somewhere between 0 and infinity. Where? Well, that's the third term right here, of course. Whenever this is 0, and that is going to be 0 when r equals a0. Because then you get 1 minus 1 equals 0. So, the answer here is r star equals a0. That is an expected result because the most probable radius of the hydrogen atom is the Bohr radius. That's the definition of a Bohr radius. It's the most probable radius of the hydrogen atom. Okay. Next, we illuminate this poor little atom with light. The photon has a wavelength of 121 nanometers. And what happens is that this electron is going to go to a higher state. So I'm going to excite the hydrogen atom to another state. The question is, which state is it? It's not given. I have to determine that. I have to determine which state, which basically means what is n? What is the principal quantum number? Because that's the key number in a hydrogen atom. The energies in a hydrogen atom only depend on n. So my task is to determine what is N. What is N of the ground state, folks? 1. Okay, so the photon number is 1 and it goes to something else. 2, 3, 4, 5, we don't know. But it depends, of course, on the energy of the photon. Okay? The energy of the photon is going to be added to my atom. So that my first task is what is the energy of the photon that is exciting this atom? I can do that because I know that H times C divided by lambda is the energy of the photon. And I can compute that because I have an actual value for lambda, and for H, and for C, and therefore my good friend the calculator could tell me what the energy is. 1.64 times 10 to the minus 18 joules. Sanity check, if you do a numerical calculation, is the number that comes out sensible or not? You want to be in the range where you expect the number to be. And it's in the range 10 to the minus 18 joules, which is a number I've seen before. The energies in the hydrogen atom are of that order. The binding energies are of the order 10 to the minus 18. Because the ionization energy, the Rydberg energy, is 2.18 times 10 to the minus 18 joules. So that is the order of magnitude of the energies, the binding energies, in the hydrogen atom. And I expect something similar. If this energy will be completely off, then this would not be an energy of relevance to exciting an electron in the hydrogen atom. But it is, so that's good. I'm feeling I'm doing the right thing here. The next thing is I need to know what is the energy difference between two states in the hydrogen atom. Namely, from state 1 to another state. Okay, well I can write it as in this way. HCr, that is the Rydberg energy. And then 1 over n squared minus, this is the final state, 1 over n squared initial state. Okay, that's the general formula for this. The energy difference between consecutive states. Fortunately, I know that I'm starting in state 1, so that's going to be HCr n squared minus 1. So my job now is to determine n, and I can do that because this energy difference between consecutive states needs to match the photon energy. So that's going to be 1.64 times 10 to the minus 18 joules. What is the value of HCr? That is the ionization energy. That is 2.18 times 10 to the minus 18 joules. That's the number. Okay? So this number is actually negative 2.18 times 10 to the minus 18. So you can divide that out, put it on this side, and the only thing you have to do is to isolate n. N squared, you take the square root, and you find n equals 2. It's a number that's like 1.999. That's 2. It should be an integer. So that's good. And I expect a number that is very close to an integer. If it's not,
Why is n is 2?
okay, well you want me to write it out explicitly, the whole thing? It's fine. If you insist. So what I'm seeing is 1 over n squared minus 1 equals 1.64 over 2.18 times 10 to the minus 18. Okay, that is my step. Do that. Then this guy is going to go right there, comes plus. Alright? Then you take the inverse in the square root and you find n. Okay, so next, what is the new most probable radius of the electron? This is kind of the same calculation we did before, but now the electron is in another state, namely n equals 2. Okay, so I'm going to just do exactly the same calculation as in question A and see if there's going to be a difference or not. I expect yes. I expect the most probable radius to be a number that is not smaller but higher than the Bohr radius, yes.
Is the most excited, like when they ask for the most excited state, do you just mean like the principal quantum number, or do you mean like the orbital that it's most likely to be in? Because it goes into the 2p orbital, right?
I can only say something about n. I cannot. Yeah, that's true. It goes in the 2p orbital. Yeah, not in the 2s because delta L equals 1. That's right. So correct. N equals 2, and L must be 1. Okay, so it's a 2p from the 1s to the 2p. Okay, so I'm going to do the same thing for this question C. I'm going to write it out. I'm going to find my function R for n equals 2. N equals 2 and L equals 1. And I see the following. I'm squaring the whole thing. And find that R, the radial distribution function, has the following form. My next task is to take the derivative of this. So let's do that. I'm going to use the product rule once again for taking the derivative. And I find this. This must be 0, and it's pretty much the same structure as in question A. Okay, again, I see something that is going to be 0 when R equals 0, or infinity. Those 2 points I can discard. And I'm focusing on the third point, which is defined by this equation right here. 4 minus R over 0, A0 must be 0. And that happens when R equals 4A0. So 4 times the Bohr radius of the ground state. So in the excited state, the atom is bigger. Okay? The atom is larger when you excite it. You put energy into it, the electron clicks into a higher state, and that state has a larger size with the most probable radius that is larger than the radius of the ground state. No?
So true.
Why was L equals 1 not 0?
Okay, let's get into that. Are you ready? This is like dpr over dr. Yeah. Okay, so I started in the 1s, and then that's of course n equals 1, n equals 2, it goes there, n equals 2, but of course I have several possibilities. I have the 2s, and then I have the 2p. Okay, so where does it go? I know it's a level 2, but it must of course go from here to there. So it sits in either one of these p orbitals, because delta L must be plus or minus 1. Okay? L in S is 0, and L over here is 1, so that transition is allowed, but you cannot go from here to here, because then delta L equals 0, and that's a no-no. So now, taking the spin-over coupling into consideration, give the term symbols for the level to which we just excited the electron. This is very similar to the question 6, the problem 6. Because what I have here, I have L equals 1, S equals 1/2, J equals 1/2, comma 3/2. Therefore, I find P2 1/2 and P2 3/2. Very similar. When a single electron sits in a P subshell, then these are the two term symbols. True for one electron, no longer true if you have more than one. But for one, I always find this. Every time a single electron occupies the P, and there's no other electrons I have to worry about, then the term symbols are always these two guys. Because these are the quantum numbers for that situation. Final one, before we depart. What is the energy separation between these two states after splitting by spin-over coupling? So what is the energy difference between these two states? That's what I asked to compute. How do you do that? We've done that in class and also on one of the worksheets, I believe. And the formula should be given on the final. It's part of the sheet in the back. It's basically the spin-over coupling energy. Your task is to fill out the values in that equation and give me the energy. Okay? So I'm going to quickly write it up. It's just literally filling out the formula. Spin-over coupling energy from that formula in the back. You don't have to think of it yourself. You can just look it up. J1 minus 1 minus. That is the formula for spin-over coupling for each state. What I have to do is, I have to calculate this value for two situations. What? Well, these L and S values remain the same for both term symbols. Because in both cases, S is 1/2, L equals 1. The only thing that changes between those two states is J. I have the value 3/2 and the value 1/2. Okay, and then I subtract the difference, or subtract one from the other to determine the difference. So if I subtract one from the other, and L and S stay the same for two situations, nothing depends on these two terms. Okay, I can just cross them out and just focus on this term right here. So what I'm getting is delta equals 1/2 HC with this funny A in front, and then I have 3/2 plus 1 minus 1/2 plus 1. That's what I have to compute. Okay, this is the J value for one of the term symbols. That's the J value for the other term symbol. The L and the S are the same, so I can forget about those. They will subtract out. And I can basically compute this expression here. And if you do that, you find 3/2 HCA with a little wiggle. And that's the answer.
Wait, why is there no S?
Oh, because they're the same.
There's two values of J.
So there's 1/2. This value doesn't change, that value doesn't change. They're at the
1/2 and 3/2. Those are two values for J.